So what I would like to discuss now with you is some design considerations from the controller. Basically, we are going to put all kind of knowledge that we gathered in the course, we are going to put it together. The input stage, what can we say about the input stage? Well, the most important performance aspect of the input stage is noise. And it will be explained in a few lines. So the stage type, the preferred stage type is CS, or a balanced common source stage. If we want a CMOS, of course, otherwise it would be common emitter if you do bipolar transistor. And why? Because it is the best nuller-like stage. And if we have a nuller as the first stage, maybe remember this from the first class, if the first stage would behave like a nuller, then the noise of following stages does not contribute at all to the equivalent input noise. Basically, you have an infinite gain before you add new noise sources, and then they will not contribute to the input noise. So we want to have the best nuller-like stage. So that is a stage without feedback, because if there's feedback, it's not a nuller anymore. One of the parameters is increased by negative feedback. So that's why CS, or balanced stage, is preferred as input stage. So what is the design? Well, we did already design of an input stage. We are going to design W, L, and the operating current so that we can have the desired noise performance. The output stage. The most important design aspect for the output stage is its drive capability. So if the output stage cannot deliver the voltage and current drive capability, there's no way. Of course, you could exchange voltage and current with a transformer. That's included in the consideration. So the stage type, again here, we want a CS type stage, but prefer this complementary parallel CS. Why? Because it has a higher efficiency. And why a CS stage? Because it is also a nuller-like stage, the best nuller-like stage you can have. Parallel, complementary parallel, I told you already, because it has an improved power efficiency if you compare it with a CS stage, if it operates in class AB mode. It is not necessary. If you operate it in class A mode, then at least you have two transistors contributed to gain instead of one. And even then, in most cases, such stages are better. So how do we design it? Well, we use the smallest length, and we need the lowest drive requirements for this stage. And then we design for the P and the N, the width, the voltages, and the quiescent current, which is common for both. Why would we want to have a nuller-like stage here as well? Maybe that is still an open question for you. Well, if we don't have a nuller-like stage, it needs an input signal. If it is a nuller stage, if it would be a nuller, it doesn't need an input signal. And the only cause for distortion is found in the output stage. So the best stage is the stage that looks like a nuller. And that is the CS stage, because all other feedback stages, of course, or balanced versions, because feedback stages have one of their parameters increased because of negative feedback. You see, this is how we combine all the knowledge that we did without doing excessive calculations on all those stages. We now find what we need to have. And we already have studied those stages, so we can use those conclusions. So we can make a single stage, maybe a single stage controller, if the noise and the drive capability can be met with a single stage. We can use a dual stage. If this is not the case, then we can make a dual stage. And then the noise performance must be met, of course, and the VI must be met, and the first stage must be able to drive the second stage. So the second stage drives the load, and the first must drive the second stage. And in multiple stages, you can just go on with this. It means the noise performance must be met, but that is usually the first stage. The one stage must always drive the next stage, and the last stage must drive the load. But you can all those things are only feasible if the midband loop gain is okay, the loop gain pulse product is okay, and the differential error to loop gain ratio is okay. One stands for accuracy, the midband loop gain. Second stands for the bandwidth of the amplifier, and the third stands for the weak nonlinearity of the amplifier. So if you make a single stage solution, noise is okay, drive capability is okay, but one of those other three aspects is not, you have to go to dual stage. If with a dual stage, noise is okay, the first one can drive the next one and the second stage can drive the load, but still it's not accurate enough, the bandwidth is not good enough and the distortion is too high, you have to go to multiple stages. And this goes on and on.